Hi everyone, this is Dave Sate. I'm very excited today to talk about our work on learning the legibility of visual text perturbations, with thanks to my co-authors Rickard Sturborg, Danish Pruthi, and Bhuvan Dhingra. So let's start with some context setting about this work. Visual attacks. These are attacks where a person replaces some characters in their message with similar looking characters to avoid automated filters and other text detection algorithms. These attacks are as old as the internet. As filters and defenses are developed, the perturbations become more sophisticated. So they started off with ASCII perturbations in LeetCode in the 70s and 80s, and have now evolved to more sophisticated Unicode substitutions in these examples from Twitter. These users are employing sophisticated techniques, like replacing letters with similar looking letters from totally different languages, or even mathematical operators like the double integral. Sometimes they even replace multiple characters with a single character. And beyond social media, we also see this in popular video games played by hundreds of millions of children, and also spear phishing emails to academics. All of these examples are to show that there are real-world stakes that motivate us to analyze these visual perturbations. And here is the academic context. So an obvious starting point is to recognize that it's only useful for attackers to perturb text to the extent that the recipient can still figure out the intended meaning. Because if the person on the other side can't reconstruct your original message, then the attacker can neither fool someone nor communicate with someone. Hence, the upper limit for perturbation must be some constraint related to human perception. And we think the obvious constraint to think about here for written text is the idea of legibility. This has not been studied systematically in the literature. In the literature, the legibility of perturbations in these visual attacks is usually enforced by some loose intuitive assumptions by the authors about what kinds of transformations to text are likely to preserve legibility. And what happens is that this often results in very conservative attacks, like substituting only one or two letters in a word, or doing simpler substitutions like adding accents to characters and so on. What we don't know is what is this sort of a holistic view on what the landscape of legibility is like and what kinds of perturbations compromise legibility. We also don't know if it's possible to automate legibility classification. Like, is legibility something that can even be learned by automated models? We try to answer both of these questions in our work. And so our work has two major categories of contributions. The first is we try to understand this notion of legibility defined by human subjectivity. And the second is we try to learn models that can align with these human notions of legibility. And to understand legibility, we try to first create more sophisticated perturbations than previous work. And by more sophisticated, we mean less rule-based, more diverse, and more effective at attacking models. And then we create a data set of people's legibility preferences over these perturbations. Now, second is learning models for legibility. So we define two tasks. The first is legibility classification, and the second is pairwise ranking of perturbations. And we'll get into both of these tasks later. Then we train text and vision models on these two tasks, and then compare our perturbations combined with our legibility classification models, and try to compare this holistic attack with existing attacks. So getting to the first step of this, how do we generate perturbations? We essentially do a one-for-one letter substitution, where given a word, it can be, the letters in that word can individually be replaced one for one by other letters in this Unicode range, which covers over 100 different scripts and languages. And so the first step is to create character level embeddings of each letter in this entire Unicode range. And we use three models to get these embeddings. The first is clip, the second is trocr, and the third one is what we call image dot, which is essentially a naive model that just renders a bitmap of each character in the Unifont font, and then just flattens that vector and considers that as the embedding. The second thing we do is to use these embeddings for each model to create a nearest neighbor space for all these characters in the Unicode range. We create one space for each of the three models, and to do that, we use the model's embeddings for each character and with cosine distance as a metric. And then the last step is to start sampling characters, which we do based on two parameters, n and k. So n is what fraction of characters do you want to substitute in a given letter, and k is for each letter you substitute, what is the distance to the nearest neighbor, the kth nearest neighbor that you substitute that letter with. So this is how we generate perturbations. And you can try this yourself by scanning the QR code and looking at the demo, where essentially you can enter a word and we will show you 10 generated perturbations using this technique. And you can even see the legibility scores for each of those perturbations. So I would recommend scanning the QR to check out the demo. Now, once we generate perturbations, the next step is to collect data. So we collected data using Amazon MTurk. On the left side, you see the annotator interface. The annotators see a pair of perturbations of the same original word, and they can click on one of four options. Either they can click on the word that they find more legible, the perturbation, or they can maybe find them equally legible, or they can find both of them unclear, and they can select that option. So using this setup, we collected around 22,000 data points, from which we were able to extract 30,000 examples for classification and 14,000 examples for ranking, with triply redundant annotations for the test set in each case. Now we take the data from this and we use it to train models to do two tasks. And these are the tasks. So there's classification and ranking. With classification, it's very simple. Binary classification is given a perturbation, is this legible or not? And for ranking, it's given two different perturbed versions of the same original word, which perturbation is more legible. As part of the tasks, the models are also allowed to condition on the original word. So the figures you see here are the actual inputs that the models see. And why did we choose these two tasks in particular? So consider the space of all perturbations of a given word. Now within this space of all the perturbations around a word, we're trying to characterize the subspace of all the legible perturbations around that word. And we think that the classification task helps us to learn the boundary of the legible region in this perturbation space, whereas the ranking task helps us inside the legible region by giving us some notion of distance inside this useful region. And so on these two tasks, we trained these two models using the dataset. These are the two supervised models we use to fine-tune. We take the pre-trained models and we fine-tune them on our data, and with some slight modifications in the loss functions and so on. So on the left, we have adapted TROCR into a dual encoder setup with different loss functions for classification and ranking tasks. We also have a third multitask loss function, which adds the two types of losses and can train on the entire data set. So those are the three losses on the slide there. And then on the right, we have Byte5, which is a token-free model, so it works particularly well with just free-form Unicode input. And for Byte5, we have a sequence-to-sequence setup where the input pair is fed in as a text prompt, and the model outputs a number indicating the predicted label. And we fine-tune this using just the default cross-entropy loss. And with these two models, we're able to take the scores from these models, from the TROCR model specifically, and calculate the legibility score for a given perturbation. And I would, again, encourage you to scan this QR and check out the demo, where you can enter the word, get perturbations, and then also see the legibility scores for each perturbation. Now, we can see qualitatively in these figures that as we go from left to right, bottom to top, the model score increases in line with our common sense judgment of legibility. These are detailed results now, where we see that for each of the two tasks, TROCR performs best overall, and specifically training on the multitask data, so that's the TROCR MT, which combines both the loss functions, that yields performance gains over all the single task models. Now, interestingly, we also see that Byte5 performance is competitive, which is interesting because Byte5 is a text-only model and never sees the actual shape of the characters, implying it learned something about visual similarity just from the pre-training corpus. Now we move on to comparing our perturbation technique with existing attacks. So our perturbation strategy, which we call the legit strategy, is basically to take a word, perturb it using the nearest neighbor maps that I was talking about earlier, and then run it through the TROCR empty model to get a legibility score. If it's not legible according to the model, then we discard that perturbation and we keep generating perturbations until we find one that is legible. And due to this, our technique can be a lot more effective at generating useful perturbations. Now, in the leftmost chart, we perturbed the Jigsaw toxic comment classification challenge using Legit and Viper, which is another existing attack in the literature. We compared the state-of-the-art model on the Jigsaw toxic comment classification challenge. This model is called Detoxify. We compared the performance of this model on each of these perturbed datasets. And we find that the legit perturbations degrade model performance the most, which is the green line here. Now, in the rightmost chart, we perturbed words using both Legit and Viper, And then we prompted GPT-3 to recover or unperturb them, which is what we call the perturbation recovery task. We find that the legit attack is much more effective at lower n, which means that it needs to replace fewer characters in the word to achieve the same effectiveness as Viper. That is to say that it achieves the same reduction in GPT-3 accuracy on the perturbation recovery task, even though it perturbs the words to a lesser extent. Now, moreover, while legit perturbations degrade model performance more, they're also more legible at the same time. So we see that qualitatively, the bottom text on this slide is much easier to read. And that's the perturbation of that paragraph from legit. The top text is from Viper, which we see is much harder to read qualitatively. So in conclusion, we find that legibility preservation is a useful framework to think systematically about visual text perturbation attacks, because it allows us to consider the entire space of perturbations that models need to defend against. And we think that future research in this area should strongly consider orienting itself using this framework of legibility. Now, we also established that models are indeed able to learn to classify and rank perturbations in a way that's well aligned with human preferences. And finally, we show that existing attacks are inefficient at exploiting the perturbation space. This is because they have to be conservative by design, since they can't do automated verification of legibility at runtime. And since we are able to automate legibility classification, we can keep generating riskier and more extreme perturbations and still guarantee that eventually we'll find a legible perturbation at that more extreme end of change. So with that, once again, I would encourage you to check out the code and demo by scanning the QR code, and thank you from all of us for your interest in our work.